In the last lecture we discussed about requirements of deriving a stiffness matrix from a fundamental principle. We already stated Kij being the element member of a stiffness matrix is nothing but the force at ith degree by giving unit displacement, okay, for unit displacement at the jth degree, keeping all other degrees of freedom restrained. So, we picked up a beam element, we showed you how one can derive the first column of this. So, now we will pick up with the same problem in the TLP. So, we know that TLP comprises of pontoon and column members. I will pick up a square plant shaped TLP where all the corners are having column members of circular in shape and all these are pontoon members. And the typical elevation of this looks like this. This is the top side, multi-level deck. Let us say these are my column members, these are my teethers. Let's say this is my mean sea level. Let me give some nomenclature and designation to this. This is of course the plan, this is the elevation. Let us assume that the TLP is subjected to unidirectional wave in this axis. This is the wave propagating direction. I call these members as 1, this column member as 2 clockwise. So, this column member as 2, this as 3 and this as 4, and assume a symmetric geometry. Let us say this becomes my x axis, this becomes my y axis in plan, and of course this becomes my z axis in elevation. The dimension of TLP centered center of the column along the wave propagation is taken as PB. PB, B stands for the breadth of the platform, P is the plan, let us say, and the dimension normal to PB, that is normal to the wave propagation, is taken as P suffix L. L stands for length of the platform and P is again the plan. So, this becomes my surge axis. I am subjecting it to unidirectional wave. So, when you draw an elevation, this column becomes 1, 3, 2 is hidden, this column becomes 4 and 3 is hidden, and this becomes the water depth. That is my pontoon member. Let us say this is my CG somewhere here, let us see. So, I give unit displacement in the x axis. The cables are inextensible, they do not get plugged off from the location, and we all know in classical terms this is what we call as offset. This is what we call as set down. Which is indicated as delta in the nomenclature. An offset in my case is the degree of freedom x1 let us say to this CG to this CG, this is x1. So, by derivation or definition this should be unity. Initially there were some tension in the cable which were nothing but T naught, where T naught is the tension per cable or per tether. Now, since the length of the cable or the tether is inextensible, obviously this tension now will be different. I call this tension as T naught plus delta T1. Delta T is the increment respect to T naught and 1 stands for the surge degree. I call this angle Now, from the physical observation we can understand that there will be forces in such direction because it has to restore. There will be force in heave direction because there is set down happening which is coupled to offset. Let us try to find out these two first, which I will call as K11, which I will call K31. The second subscript 1 stands for the first column of the matrix, which also tells me that I am giving unit displacement about the first degree of freedom, and the first subscript of 1, 3 etc. are the respective degrees of freedom where we are measuring the values. To be very clear, we know this, that this is what we are measuring. This is x, let us say this is y and this is z, this is surge, this is sway, this is heave and this is roll. Put a thumb towards this, 4 fingers will point out this. This is my pitch and this is my yaw. These are the degrees of freedom which we are actually measuring, and the point we are measuring is nothing but the CG of the platform where we are trying to measure. One can ask me why you are not bothered about the tethers. We are not talking about tether displacement, we are not talking about the hull separately, we are talking this as a rigid body motion. The pontoons and the columns and the deck move together as a rigid body, they do not move separately. So, let us quickly find out the increase in tether tension delta T1. Is nothing but the change in length with the A by L, that is axial stiffness of the member. Change in length from here can be easily found out as x1 square plus L square the root of that minus L, that is the change in length, multiplied by the axial stiffness will give me my delta T1. Now, this tension has got an horizontal component, vertical component. Horizontal component is the restoration in surge axis, vertical component is the restoration in heave axis. So, let us talk about the horizontal component. So, that component is going to be the force in x axis multiplied by the displacement, that gives me the force now, because stiffness Newton per meter, which will give me the force now, which should be actually equal to T naught plus delta T1. If this angle is gamma x, this is also gamma x by symmetry. So, I should say sin gamma x. Now, since I am saying T naught and delta T1 is the axial tension in each tether, I should multiply with 4 sets of such value, because there are 4 such sets, and from the geometry sin gamma x is nothing but x1 by L, or let us say L, will replace L with root of x1 square plus L square, that is a new length. So, now I can easily get K11 as 4 T naught plus delta T1 x1 square plus L square. So, K11 4 times of T0 plus delta T1 by root of x1 square plus L square, where L is the length of the cable or the tether. If you look at this figure, the platform does not move normal to the board, so there is no save movement. So, K21 is going to be 0 because there is no sway movement, since the wave is unidirectional. It is an assumption that the wave is hitting the platform only along x. There is no angle of attack. Now let us talk about the force in the vertical degree, that is heave. K31 should be the force multiplied by the value in terms of displacement of heave. So I should say in heave axis let us say along heave direction, K31 multiplied by delta, because that is the set down effect we have here, that is the displacement. Now this should have a component in the vertical direction, the component resolved in the vertical axis, which is going to be cos of this value. So T1 or T0 plus delta T1 of cos gamma x of 4 times minus T0, because I am looking only for the increment. Initially it was in pretension, so I do not have to use T0 as such, because T0 was not contributed because of the movement of x1, because when the x1 was not happening, platform was stable and T0 was imposed already in the platform. So T0 is not a component of x1, or T0 does not arise because of x1. The one which is causing or influenced by x1 is delta T1. Okay. So I have to subtract that. So cos gamma x again is L by root of x1 square plus L square. So substitute back here. So I will get K31 delta as 4 T0 by delta T1 of L by root of x1 square plus L square minus 4 T0. Okay. So I can even do this as K31 is 4 T0 minus 1, can even say 4 T0 cos gamma x minus 1. I am just replacing this value back as cos gamma x for simplicity. Cos gamma x minus 1 plus 4 delta T1 cos gamma x, the whole divided by delta. Where delta is what is called set down effect. So we have K11, we have K21, we have K31. Since K21 is 0, K41, you must understand that there is no force in the y axis, therefore there is no moment about x axis. So rho will be 0. Since there is no force along y axis, there is no moment about x axis. Since there is force along x axis, there will be moment about y axis, there is pitch. So resolving along pitch axis. So K11 is going to act this way. One can ask me a question, I have marked the direction. Force is always happening only in the displacement in the positive axis. For example, take a beam, you give a displacement this way, so you have a displacement this way. So the force always in the direction as that of the displacement. You cannot always have a force opposite to displacement, at least in the first value. And we also know that K11 being the diagonally dominant member in the matrix, it has got to be positive. Okay, it cannot be negative. So K11 is marked this way. If I call the distance of K11 action, which is going to happen at CG with respect to keel in the new position as h bar, which is also same earlier, and K51 is a restoring component. Okay, you can look at the original degree of freedom, K5 is restoring, therefore K51 is now going to be minus K11 of h bar. So, K 5 1 I have, K 6 1 is going to be 0 because the platform is symmetric. On the other hand, look at the geometry, 1 2 3 4 all pontoons are equally spaced from the CG being a square platform. I have taken a dimension of PL and PB knowingly, but let us assume it is a square platform, they will have a symmetry. Even if it is rectangular, they will be symmetrically placed otherwise also. The diameters are same, pontoon dimensions are same, therefore, absolute there is symmetry in geometry, the platform will not yaw. So, K 6 1 is 0 for a given x 1 displacement. So, we have all the 6 values available in the first column of the matrix 1 1 2 1 3 1 4 1 5 1 6 1. Now, we can enter them and we get the first column of the matrix. Similarly, if you want to give or derive the second column of the matrix in the sway direction, instead of giving displacement along this, I must give displacement along y. So, if I give displacement along y, then I have to draw a view from this direction. So, the right hand side will be 2, if I am drawing from here, left hand side is going to be 1, right hand is going to be simply 2, and I can say this is x2. I get the same equation back again, only thing is I will change the nomenclature slightly for a sway motion, which I am doing it here. So, for sway displacement, that is displacement along y axis. So, the same figure holds good, except that I will change the nomenclature slightly, I can rewrite the equations readily. So, I will get K 2 2, K 1 2 will be 0 because no force along x, because of displacement caused along y. Okay. Force is already acting along x, there is no movement along x because of displacement caused along y, okay, because we have to keep all other degrees restrained. There is a derivation fundamental in stiffness matrix. So, K 1 2 is going to be 0, we can always see there is a symmetry, K 2 1 was 0 and I am getting K 1 2 back as 0. So, it is a full symmetry of the matrix. Okay. K 2 2 is going to be similar to that of 1 1 except the nomenclature will change. So, I will say simply I will use the same nomenclature there, 4 T naught plus delta T 2 because I am giving along the y axis the second degree root of, instead of x 1 I will say x 2 square plus L square because S 2 is the displacement I have given along y, and so on. Similarly, when I move along y, there will be offset along y, there is going to be set down along y also. So, there is going to be an influence of this y movement along the z axis which is in the heave direction, therefore, there will be K 3 2 which is the same as K 3 1, which is going to be 1 by delta of okay, I will write down from here 4 T naught cos gamma y minus 1 plus 4 T 2 cos gamma. The angle is now going to be gamma y when I am going to give displacement along y axis, going to be delta T 2, isn't it? It is going to be delta T 2. Now, I have no force along x, therefore, I will have no moment about y, therefore, K phi 2 will be 0, no pitch, and K 4 2 will be as similar to that of the pitch moment earlier, which is going to be minus of K 2 2 of h bar, same as that of the earlier case, and K 6 2 is going to be 0, the platform is symmetric about y axis, there is no movement. Now, I have all the columns. Now, the second column 1 2 2 2 3 2 4 2 5 2 and 6 2, I have the second column of the stiffness matrix now for the TLP. For heave displacement, that is displacement along displacement x 3 along z axis. all these displacements are along the positive axis respectively. If I purely give displacement only along the z axis, let us say only along the z axis, assuming that the platform hypothetically does not move along x and along y. So, the platform will remain like this, not like the yellow one, but the platform moves only up and down. There is going to be a draft variation alone, which will affect the submerged volume of the pontoons and the columns. Okay. So, the restoration force in the heave direction is going to come only by the change in displaced volume of the submerged members of 1 and 2 or 1 and 4, whatever may be the direction we look at. Okay. All the 4 will become effective now, because the platform is ideally moving only along the z axis. Therefore, K13, there is no contribution in surge direction because of the movement in the heave direction, 0. Similarly, K23, there is no sway force because of heave movement, 0. K33 delta should be now counteracted by the initial tension in the teethers, which is AE by L of 4 teethers plus the submerged volume okay, where DC is the diameter of the column. C stands for the column. Pontoons anyway completely submerged, they will have no variable buoyancy, only the column variation will be there, that variation nothing but delta. Okay, that is the degree we are given, where delta is unity in this case by derivation, because I have to give a unit displacement to get the force in heave. Okay, I am just pushing the platform only in the positive heave axis. Ideally speaking, it does not move along x and y. Okay. And obviously, since K13 is 0, K43 is 0, since K23 is 0, because roll and sway are associated. This is sway, this is roll. If sway is 0, roll is 0. K53 is 0 since K13 is 0, because pitch and surge are associated. When you give surge, it causes a moment about y axis, which is nothing but the pitch. Because of symmetry, the platform does not yaw because of symmetry. So, this is 0. So, I have got the third column of the stiffness matrix now, where only 3 is present. Let us talk about the roll displacement. Any doubt till this point? Now, we are talking about rotational displacement. I have given the translation displacement along x, along y and along z respectively. I have got the coordinates, or I have got the members of the stiffness matrix for the first 3 columns. Now, I am going to give the roll displacement or roll rotation. Fall, roll, let us say rotation. So, let us draw the diagram now. Let us say this is 1, this is 2, this is 3 and this is 4, and this is PB and this is PL. This is my wave axis, which is x. This is my plan. This is DC, diameter of the column, this is diameter of the pontoon. Ideally speaking, in all TLPs usually they are kept same, because they will have fabrication difficulties at these junctions. Okay, they are taken almost same in all the cases usually. Now I have to give a unit roll. The roll means it has to be rotated about this axis. Okay. So I have to draw the view from this direction. My right hand side column will be 1 and left will be 2. Let me draw that here. Strictly speaking, the centered center of this will be actually PL. I am looking from this direction, I am looking for roll. This is pitch. Moment about this axis is pitch. I am looking for this axis. Okay, I have to draw this view. So I can call this member as 1 and this member as 2. So now this rolls. Let us now mark the rolled value. This is my pontoon. Let us say I have the CG at this point. Now I am drawing a new configuration. This is 1, this is 2. So let us say this is my CG. I call this angle as theta 4. So K44 will be responsible for this theta 4. Now obviously you see the column 1 is submerged more compared to that of column 2 now. So buoyancy force is nothing but an upward force acting on the submerged volume of the member. The moment the member is submerged more compared to the other one, initially the buoyancy was coplanar and collinear with center of gravity for static stability. It will now move towards 1. Okay, because 1 is submerged more compared to 2. 2 is lifted up as per this configuration. So I mark the new value of FB. Let us try to extend this slightly. Extend it here. Okay. Let me mark the new value FB here. This is my new value FB, which was the original value here. I call the offset of these as E suffix 4. 4 stands for degree of freedom 4, which is roll. E is the eccentricity. Now how this has been caused? How you are able to give this rotation? It is because when you give this rotation, obviously this cable what you have here will be pulled off more. Let us mark this. Will be pulled off more, which will be T naught plus delta T4 dash. I will come to what is dash means. And this cable which was here, which is T naught plus delta T4 dash. Initially they had only T naught plus delta T4 and T naught plus delta T4. Now the difference between the tether tension variation with and without roll is that delta T4 dash only. Okay, this is what it has caused the rotation theta 4. Now from the CG I call this force as S1, the distance, this as S1. I hope the drawing is clear. From the CG I call this as S1, not from the buoyancy center. From the new buoyancy center I call this as S1, this as S1. Of course this is E, which we already have here. And the remaining distance for the new one is what we call as S2. So S1 is the distance of the theta from the new buoyancy force center. S2 is the distance of the theta, we can say attached to column 1, this is column 2, sorry, column 2, this is attached to column 1 from the buoyancy center. E is the offset which is created or resulted from shift of buoyancy from CG. So this is not developing any force along x axis, therefore I should say K14 is z to 0 because no force is developed along x direction. K24 is also 0 because there is no force developed along y direction. Now let us see what is the change in pretension. The change in pretension delta T4. I am talking about delta T4, which is change in pretension caused because of the roll. Which should be actually equal to half of this dimension of cos theta 4, that is going to be the x component of this cos theta 4, of course multiplied by the initial axial tension available in the cable. Now one can ask me a question, what is the difference between delta T4 and delta T4 prime? Delta T4 is constant and equally get involved in all the legs because of the roll moment. Delta T4 dash is only on those farthest ethers. Okay. So delta T4 ideally speaking is taken same as that of T4. So we assume that the tension change in the farthest leg is as same as that of the nearer leg also, because the platform is symmetric, that is why I am using PL by 2 here. Had this been a triangular one, then I would see the tension in the nearer leg will be different than that of the farther leg. Okay. Or if it is PL and PB and they are rectangular, if you look at this dimension it will be different, this dimension will be different. So we are assuming that the platform is symmetric initially at PL by 2. Since I am using PL by 2, I assume that the change in the nearest legs and the farther legs, which are delta T4 and delta T0 T4 prime, are same in all the legs. That is why I am multiplying this by 4. So I should now get K34, that is the force in the heave degree because of the roll given in the 4th degree of freedom, which is going to be delta T4 plus delta T4 dash, because this is going to be only nothing but the change in tension, that is all, because the change in tension alone is actually rolling the platform. Okay. Since I have got 2 near tension and 2 farther tension, I will multiply this by 2, okay, and I will divide this by theta 4 for dimension symmetry. Now let us understand how to compute K44, how to compute K44. Now there are two components involved in this. One is the set of these two legs. What are these two legs? For example, 2 and 1, 2 and 3. I am looking this platform from this direction. 2 and 3 are overlaid. There can be tension at 2, there can be tension at 3 also. They will have moment about this Fb of a distance S1, and theta is attached to column 1 and 4 which are overlaid will have moment about Fb again, which is distant at S2, and S1 and S2 are not equal because they are offset by E. Initially they were equal, which are nothing but Pb by 2, which were equal to Pb by 2 because all tension were same. Now it is not, okay, because there is an eccentricity, because this column is getting submerged more compared to this column. On the other hand, 1 and 4 are getting submerged more compared to 2 and 3. Therefore, there is going to be a change in tension marginally between these legs of tension to the top of these legs. Therefore, there is an offset of Fb. Fb initially shifted from here towards this, and that eccentricity is what E. Now I am trying to work out the moment. Why I am working out the moment? Because K44 is a restoring moment in roll degree. So for K44 of theta 4 should be equal to, this is anti-clockwise, you can see this is clockwise, will be equal to now this is tension in the cable, and this is the point where Fb is acting. Fb is acting this way, this is my buoyancy force. So this is clockwise, Fb is having eccentricity with Cg, which is E4. So Fb of E4 plus T0 plus delta T4 dash twice, I am talking about this leg into S1 minus E4. I am talking about this leg, which is counteractive to K44 like Fb, okay, minus. Now I am talking about this leg, this one. So I should say T0 plus delta T4 prime of S2 plus E4 of twice, okay. I will get K44 now. K14 was 0, K24 was 0, K34 is obtained, K44, K54 and 64 were 0 due to why K54 is 0? Pitch was 0 because there is no sway, okay. Similarly, K64 is 0 because it is symmetry. Now in this equation you see Fb is known to me, that is a buoyancy force which is known to me for a given system of displacement. T0 is of course initial prediction given to the system, okay. S1 and S2 are geometric values. If you know the plot, you can easily find out vectorially what is the shift of S1 and S2, because you have to find out the E4 value. If you know E4, then now how to compute E4? Now how to compute E4? The angle is subtended from the center, from this center to this center. Look at the half of the portion. So I have to plot it here. If this is E4, this is the eccentricity, this is my H bar, this is my theta. Okay, it is rotating about the center, half of that. So therefore, sin theta E4 by H bar. So H bar sin theta can be E4. So E4 has now become a function of displacement, because theta is a displacement now. Theta is actually a displacement, okay. Has become a function of displacement. That is the beauty of the whole problem. All stiffness coefficients rather in all the cases will all become function of displacements now. Okay, all stiffness coefficients become function of displacements. That is the beauty of the whole problem. Similarly, I can extend the same discussion for pitch. So I have to draw the figure from this view now, because pitch is moment about this axis. So 1 and 4 I will draw here, 2 and 3 will be overlaid behind 4 and 1 respectively. I will give again theta phi. I will write directly the equations for the fifth column of the stiffness matrix in the same manner. So for pitch rotation, which I call as theta phi. By derivation all these are unity, that is how you get the forces. Okay. So K1 phi remains 0, K2 phi remains 0, K3 phi will be T0 plus delta T phi dash twice of phi. K phi 4 phi will remain 0 because K1 phi is 0, K phi phi. Similar value how we wrote for K4 4. The classical derivation given in the equation shows like this: pi dc square by 4 rho wg 4 times, that is nothing but the immersed volume of Pb of sin theta phi. You can also write the similar way for theta 4 also, which is rho, plus 4 times of T0 h bar sin theta phi by theta phi, because this is coming exactly from E phi, plus four times of AE by L of, that is change in tension, which is Pb by 2 cos theta phi. You can write either K44 or phi phi in the form earlier shown to you or in this new form. One, if you substitute back, they will be exactly same. So I have now K6 phi is 0 due to symmetry. I have the fifth column of the matrix now. We have the sixth column, which is Ya. We will do that in the next lecture. Then we will talk about some important characteristics of the stiffness matrix. We will talk about the mass matrix derivation. Then we will move on to the damping matrix of TLP. Then we will talk about the solution procedure for TLP. So any doubt here? We have derived the members or elements of stiffness matrix step by step from the first principles by giving unit displacement in the respective degree of freedom, and we got the forces in the respective degrees, keeping all of the degrees constrained. Then there are some very special characteristics of the stiffness matrix members, which I will discuss in the next lecture, which is very important. Any doubt? So please look at the references available in the NPTEL. I have got a classical paper. There are two issues. One, I have my own paper with Jain, Chandrasekhar and Jain. (2002) Ocean Engineering Journal. Please see this reference, the whole derivation is available there. The other one is Morgan and Melieb, 1983. Again the reference available in NPTEL, please see that. So these are the two key papers based on which this derivation was transcribed actually. Okay. So please see these papers, you will get more. One is a conference, there is an OME Houston, the journal paper, this is Ocean Engineering Journal paper. This is of course OME conference. The references are available in NPTEL site, you please see that, you get the full reference. Locate the paper and try to read them. So you will get the full derivation and explanation of what has been discussed in the blackboard here for more clarity in terms of understanding this. So please look at this, we will continue in the next lecture.